Obviously, there are a huge number of challenges that arise in these application domains, right, pertaining to labor and the challenges of actually executing these tasks. And there's an amazing potential for automation and electrification to revolutionize these fields. But there are also various challenges that exist. And so today we have 6 experts that are working in these areas, 3 from John Deere, 3 from here in Icon at Purdue, that are going to be telling us about their perspectives, their current capabilities, and what they think are potentially challenges for the future. So the panel is going to start by having these experts discuss their perspectives. At that point, we'll have a discussion and Q&A time at the end for the audience and for the panelists to interact with each other. Okay, so with that, it's my pleasure to welcome the panelists. So we have, as I said, 3 from John Deere, Mr. Mark Cheney, Dr. Bridge Singh, and Dr. Scott Johnson. So I'll just introduce the 3 John Deere panelists all together. They will give their presentation, and then we'll go to the Purdue panelists. Okay, so Mr. Mark Cheney is leading the automation delivery systems teams at the Intelligent Systems Group at John Deere. He started his career with John Deere a long time ago, 1996, has been working on a variety of things, including harvest product development, PV&V, and he's gone from the site engineering manager to global advanced engineering manager for crop harvesting. And prior to that, he's had work experience such as experimental seed development, farming, equipment operation, and so forth. He's also a fellow University of Illinois alumni, as am I, so it's always great to see that. Dr. Bridge Singh is the Region 4 Manager, External Relationships and John Deere Fellow in Power Electronics Engineering at John Deere. He supports and leads John Deere relations with universities, as well as non-compete industries and government entities, including national labs. So before joining here, he led the U.S. Department of Energy funded projects and developed extremely power dense, high efficiency, engine coolant capable silicon carbide inverters. And prior to John Deere, he was also an assistant professor of electrical engineering and tooling. So great to have you, Bridge. And Dr. Scott Johnson is a local. He got his PhD from here at Purdue in the automatic control area from electrical and computer engineering. He's a senior control systems engineer for power electronics at John Deere. He develops new algorithms for precision agriculture, hybrid vehicles, and vehicle power management. He's passionate about the latest control methods, including our reinforcement learning, model predictive control, adaptive control, and more. So it's a great pleasure to have you all here. I will turn the floor over to you. So Mark, you may go ahead and share your screen.
All righty. While we're transitioning here, I just wanted to say, thank you for the opportunity and big thanks to the Purdue team for continuing to crank out really good talent. So next 10 minutes here, I'm going to provide an overview of why automation and autonomy is important to us at John Deere and our customers. And as we get started here, I want to kind of give you what our mission statement or purpose is at John Deere, and it is to make our customers the world's most profitable and sustainable in their industries. And what this means to our customers and why it's important to them is because they have a huge task in front of them to, not only be profitable and sustainable, but also they need to feed, fuel, clothe, and continue to build infrastructure for a growing population, which is a noble and a real cause and mission that we're on to support them in doing that. So our farming customers. Farming is a challenging job. There are lots of different variables that come into play when you are setting out to go grow a crop and take that crop off the land. It's a race against time. And not only do you only get about, the average farmer gets about 40 times to get it right, throughout their lifetime. It's a timing race within each growing season. you know, from the very beginning of planting that crop to getting it into the ground, which can be measured by days to get it right. That first, once you put that seed in the ground, very small windows of opportunity. And then it's a gamble on what the growing season is going to be like the rest of the year. So they're constantly, you know, fighting threats against weather, pests, input costs, and many hard decisions to get the best out of that seed at the end of the season. And on top of it all, they have challenges with labor, whether it's availability or skilled labor. This is a constant battle for them, along with all the other challenging decisions they need to make to get that crop out of the ground and maximize the yield. So these customers need intelligent solutions to take farming into the future. And this is where we're aiming new technologies to automate our products with the use of computer vision and machine learning capabilities. So we talked a little bit about the challenges our customers have. We are working to develop smarter equipment so they can make better decisions in each of their steps across their production system. We're not only working in each of one of these steps where we've traditionally done a lot of work on getting the most out of that piece of equipment through like iron technology. Now we're looking to get even more out of it from the automation technologies we're developing, not just to make it easier for them to do that job, but also to extract more value out of each job. You know, for example, grain quality cameras on combines allow the operator to see the grain inside the machine like they've never seen it before. So these technologies aren't just replacing their senses for operating a vehicle or a piece of equipment. It's taking them further into the heart of that job and starting to do it for them better than they've ever done it before. In addition to each step, we're finding that there is a lot of value to unlock across the steps that can complement each step. So like across the bottom there, you see, we like to make sure we are getting everything out of the pass that piece of equipment's making through the field. Make every seed count, make every drop count, and make every grain count. Data is a big thing, as probably many on this call know, and it's a large topic. Often it has been the output of what our equipment and solutions do, but really it's the fuel that's going to provide the foundation and development for future solutions. Just some scale of the data that we have in front of us right now through our operations centers. The first number there, we have 3 billion documented map layers in our operations center. This tees up data for our customers, and it provides us greater insights into what's going on with our equipments and our customers' jobs. 15 million is a number that represents how many measurements per second are coming off of our sensors in peak time. And then 104 represents the number of countries that we have our operations center marketed in right now. And this is growing. So the takeaway here is that we are building large, diverse, real data sets to really fuel these computer vision and machine learning solutions for automation. From a decision standpoint, we are really changing the landscape of agriculture with the use of these new technologies. And whether it's at a field level, a plant level, across their production system, we are starting to be able to make decisions in real time to aid them to understand when is the right time to get that seed in the ground, or what's the right time to go spray for a pest. And all this builds, like I said, across each step to help them make the best crop they can make out of that season and when to harvest it. Now switching gears to our construction and road building customers, you'll see some similarities here where they have very similar challenges, whether it's time, weather, costs, the decisions they need to make timely, and the labor. So very similar landscape and challenges for them. We are also working with them to bring this technology into their industries to do much of the same. As the need is great, they are fighting different challenges than our ag customers, but we are actually leveraging a lot of the same technologies across their businesses as well. They also have a little different challenge too than our ag customers. This is a little video of downtown Dubuque, Iowa, where some underground construction work was taking place. And just take a look at all the hazards. Safety is a big deal with our construction and road building customers. And it is one of the #1 areas we are working on with them to apply this technology. And that is why you kind of see one of the technologies in front of you here, where we're leveraging a technology that can look behind our equipment, provide alerts when obstacles are near. And this is just the start of this. Just imagine how we can continue to apply computer vision and machine learning technologies to make job sites and work sites safer. Now I want to show you a little video about our acquisition with Blue River Technology and the work they're doing to revolutionize agriculture.
We're seeing lots of resistance to Roundup. We're looking for other ways to combat the weeds and still have cost savings on top of everything.
We saw an opportunity to take cameras, computers, and artificial intelligence to allow ag machines to see every plant in a field. We thought that we could give farmers the ultimate flexible tool to treat their field and manage their field in whatever way they wanted by having the knowledge of every plant and its situation and an ability to spray very precisely, whether it be herbicide only to the weeds or fertilizer or fungicide directly on each plant that needed it.
Each field they go to has a different set of conditions, and they need to be able to adjust and correctly set that machine's performance for the field. One knob could be the protection of the cotton plant and how big of a buffer, a safe zone that we provide the plant so that when we apply selective materials or non-selective materials that we have the appropriate buffer. Another dial is how aggressive do you want to be at going after anything that looks like a weed. There's also some opportunities to inform the grower of how many weeds the system's seeing, even what kinds of weeds exist in the field, that they can start to tailor their herbicide programs towards those weeds.
The cameras and computers on a See and Spray machine are using deep learning algorithms that are similar to what's used in facial recognition. The first time we saw a pigweed, the machine didn't know what kind of plant it was, but we taught it by giving it tens of thousands of examples of that pigweed, and now it's an expert in pigweed. We save up to 90% of the amount of herbicide that you would spray if you were spraying the entire field.
The weeds have become a little bit more of a pest than what they were originally. They've become resistant to a lot of the herbicide that we've been using on them.
With the rig, we have other options open to us. We can spray different chemicals that we're not able to spray before. We can take one man and put him on a tractor, and we can do the work of 8 to 10 people.
We're seeing no end to the use of this technology. Essentially, anything that may be cost prohibitive or more difficult to do when you're spraying on a broadcast basis, but much more grower beneficial if we're spraying on a very precise basis.
So you can see tremendous opportunity for us there, and some awesome work being done by the teams at John Deere and Blue River to revolutionize our future in ag and construction and road building for our customers. And again, I want to thank Purdue for continuing to crank out great talent and know that we are strengthening our position for the future in this space. And we need folks experienced in machine automation, digital projects, and artificial intelligence on the edge. So thank you. And I'd like to transition it over to Dr. Bridge Singh now, and he's going to go into a little bit about power electronics.
Good morning. So Mark, that was very insightful, exciting presentation, and you really had the challenges our customer face, and we like to solve this problem and provide solutions. So I would be going through this silicon carbide inverter development that we did starting 2015 time frame. Next slide. So we are committed to those linked to the land. That is our slogan. And it's a demanding application of power electronics. Failure is not option for our vehicle, because when vehicle goes down, there are numerous other vehicles waiting for it, so everything is down. So failure is not think of. Whether it is silicon or silicon carbide, customer expectation is high. It doesn't matter whether you are putting new technology or adding something additional aspect in the existing technology. You just cannot get away from customer expectation. So what that means is we have to have a ruggedized powertronics with enabling control technology so we could pass on customer value. And I'm not going to play video, but you can look into the, using this link, you could see the various aspects of this vehicle. Next slide. And this vehicle, as Mark is advancing, it has seen one fleet at one customer side has seen 1 million field hour that established the reliability of the vehicle, that the powertronics that we have developed in 2007 to 10 to 12 time frame. Control system prevents near zero speed, tire spin and slicing. And the reason is that because this is one of the core benefit of electrification that we did not think of. So in the emerging technology or advanced technology development work, when we do oftentimes we find the customer value when the product gets in the field, So if there any possibility, some of the things can be understood upfront. And this vehicle has established industry-leading reliability goal by advanced control, power management, and all that. So if you click this link, I'm not asking Mark to click, but you could do that. You will see the nice story from one of our customer, the testimony on how this vehicle perform and give the value to the customer, and then how it completed the 1 million field hour as opposed to non-electrified loader, actually 24 gallon fuel per hour, similar size vehicle versus 9 gallon per fuel per hour, right? And you can imagine that what is the carbon footprint reduction and things like that, that nicely tie in our sustainability goal. Next slide. So when we began silicon carbide technology development work in 2015, we were given very aggressive target. It was funded by Department of Energy, and have not done anything silicon carbide related work before. And silicon carbide is a very advanced material, has its own challenges related to packaging, thermal management, and gate drive, and things like that. So I'm not going to read all these numbers, but very high efficiency target, miniaturization of powertrain is very extremely power dense converter. And in addition to that, going engine coolant, because in our vehicle, there are numerous cooling loops, and every one of them have their own, what you call the options. Like if failure could be a possibility that if you have a dedicated cooling loop, particularly electrical pump. So the idea was that if we could eliminate dedicated cooling pump for the inverter, that would be big value, and particularly system integration. So we did qualify this inverter can go up to engine coolant and up to 115 degrees C coolant. So what I'm talking here, 130 degrees C ambient electronics, and that has to meet that 1 million field hour reliability, right? So this is extremely challenging problem. Silicon carbide advanced technology is emerging technology for off-road vehicle application. There are some risks. One risk is that it being new in our field of use, because we have established leadership position in the electrification. For agriculture side, we are doing that X-Acto multiplanter, which Scott will talk about, and Mark has mentioned, and also then construction side. So we want to retain that position by working on advanced technology and mitigating risk, understanding supply chain issues. And once we have established the competitive advantage, it can be put for greater use. So what that is, these risks can be mitigated by what you call innovation. And that's exactly we are out doing in emerging technology organization and also advanced engineering organization within John Deere. Next slide. So what you see here is the progression of power density. Looks like on my side, two boxes are missing. I don't know, Mark, you have it or not, but what it is basically, you have PDF copy of this presentation, so you can look through that. So if you look at these are inverter, all of them are identical capability, each of them 400 kilowatt. And from each, inverter from one inverter to another inverter, every 5 years, we are cutting inverter size in half and increasing their power density, coolant capability, and also the performance. And also at the same time, we are reducing the cost of these inverters, which is extremely challenging problem. But then it comes with the benefit, like smaller it gets, better it becomes. So what that means is that once we are not very high volume business, once you basically establish one inverter and you pay down all the development cost and software and everything, and you could use same inverter, same hardware to capture the many vehicle application, that's what the modularity comes into play. So you then all of a sudden start enjoying the economy of scale. Increasing power density gives competitive advantage. Why it is so? That if box is smaller, then it is a lot easier to put it on the vehicle system integration. It's not inverter, it's going to enable a vehicle function. So that's why miniaturization is extremely important. It comes with own challenges, particularly packaging, thermal management. In addition to that, then control aspect of it and qualification and things like that. And improve performance and high temperature gives system benefits. I said earlier, what you call the engine coolant elimination, right? So that makes the vehicle system integration much easier. So I want you to comprehend the scale of this. So click one more time, mouse. Yeah, here you go. So you could imagine that now this inverter has gotten so small that you could measure in terms of iPhone. I was very curious when this box came to me, and I said, let me measure in terms of iPhone. First of all, they are reducing in size and weight, and this is just comparable to iPhone now. It's like a less than iPhone height and 2 iPhone deep, and left to right almost 2 iPhone, right? So it's very, very small. What that I'm trying to indicate here, maybe next inverter 5 years down the road may look like similar to iPhone. And that's where the Department of Energy is also heading. We have 43 kilowatt per liter power density. Department of Energy next goal is 100 kilowatt per liter power density. And then another thing is that if you look at the per capita US energy consumption, 10 kilowatt hour per day, right, per household, what that means is this box, such a small box, can process electricity worth of 40 houses. Now comprehend around your powers, substation around house, right? How big that is versus this little box can do that. And on top of that, this iPhone size power module that is inside this can handle electricity worth 20 houses. Now you should comprehend this, that how challenging packaging, thermal management, and control problem this has. And then we are trying to solve these by innovation. Next slide. did not change. Okay. So here, this is basically the comparison of all our 3 inverters. So when we began in 2015, this is another aspect that when you are working on a technology that may have a risk, not a lot of data out there, how you mitigate that risk. This project taught me that. So what we did, we took our one of the IGBT inverter and did very, impactful work very early on. What that means is, with no knowledge in silicon carbide technology, control, packaging, thermal management, devices, gate drive, all sort of things, within 9 months, we were spinning electric machine with the silicon carbide inverter. What that tells that very early on, we are mitigating the risk and we are putting our resources, all that, right? And time is essence. So if there's risk and you could mitigate and you found out that no, this is not mature enough, maybe we should slow down our development progress, right, process. So this project taught me that very early on mitigate risk and then intensify development effort. So within 4 years, we've gone from very huge box on the very left to very miniaturized inverter on the right. And look at on the bottom, 3 pictures, how easier it is to connect inverter with the motor or electric machine. So it's like easier integration on the vehicle, and miniaturization gives that advantage, but it doesn't come free. It comes with a lot of challenges, solving thermal management, packaging, control aspects, all that. Next slide, please. So I often get to ask that, okay, these are hybrid vehicle, 644, 944 loader. What is the battery size in this vehicle you put on? Answer is no battery there, only the start engine, right, 12 or 24 battery. The reason is that because these are energy guzzler, right? 944, as I said earlier, 9 gallon per hour fuel consumption. This may take about 4.5, 644. You just cannot get battery and keep working 12 hours, and 944 may work 18 to 22 hours non-stop per day. So what that means is you take this drivetrain, engine, gearbox, and generate electricity on board, and then transmission system, that's where the magic happens. And this gives operator huge flexibility, and that is by doing the vehicle power management. Automatically, there are software algorithms that are controlling and making operator to pay attention to the work versus how the vehicle is operating. So a lot of automation is helping us and making operator much more productive and performing versus paying attention to how vehicle is working. Next slide. So, that U4 boxes that you saw, PD550 to Gen 2 silicon carbide inverter. So what we did, miniaturization, one of the aspect of miniaturization was we reduced the amount of capacitor we put on the DC bus. And we gone from 13,000 microfarad to as less as 440 microfarad without compromising performance, capability, and all aspects. How I could verify that yes, that is the right thing to do. So we do a lot of simulation, hardware in loop simulation, Simulink simulation, followed by some experimentation in the laboratory, and then improve our control system, hardware, and all that. And that's how we check out that yes, indeed, going from very high value capacitor to as little as 440 gives us power density advantage. But then in addition to that, if I want to change torque 1000 Newton meter per millisecond, because that's how operator expectations are, customer expectations are. So how can this do that? And there is a lot of advancement in software needed to happen to make sure that yes, this little capacitor 440 microfarad is good to go. And what we do, basically, we do multi-machine, multi-inverter setup to pretty much simulate vehicle condition in the live environment before going and putting hardware in the vehicle. Next slide, please. So here, what you see is that inverter and motor setup. So On the far right is Gen 2 silicon carbide inverter operating as high as 115 degrees C coolant. And then the middle one is PD400 inverter. And these two inverters together are spinning 4 electric machines. So pretty much simulating vehicle condition in the live environment. And then we check out all our control, software, all aspect of the inverter development before putting on the vehicle. Next slide, please. And we have 14 such dyno in Fargo, North Dakota, where we do electrification related development work. So the vehicle operator, particularly construction and mining vehicle, day long, they are going high power to low power, stop, start, that you are digging the pile, and which is very, very taxing on the power electronics. So it has to be ruggedized to withstand those operations. So testing it that if I quickly change the power from 30 kilowatt to 150 kilowatt, what happens to particular DC bus up, because it has to remain stable to provide 1000 Newton meter per millisecond torque change. And that we found that yes, we can minimize that capacitor a little as it could be, and it reduces the inverter cost, makes it power dense, but at the same time, no compromise in the performance. Next slide, please. So this slide is the YouTube link. I don't want to play it. You guys can just dial this YouTube link in your computer and you will be able to see silicon carbide inverter demonstrated on the vehicle. And we had our Gen 1 inverter, then later on gone Gen 2. So Gen 1 is demonstrated on the vehicle, Gen 2 thoroughly tested in the laboratory environment for 115 degrees C coolant capability. We call engine coolant capable inverter. Next slide, please. So in conclusion, silicon carbide power times is real. That's what we found out by doing a lot of benchtop testing, back-to-back dyno testing, in-vehicle testing, and we have roughly 3,500 hour experience. We believe that if you take system approach, we could get by 2025 or so time frame, this technology will start competing, but it could go into some niche application, like a battery powered vehicle could be one application, could go, or maybe where motor inverter integration are must, there it could go. And then another aspect then from supply chain, we found that as compared to silicon, traditional state-of-art technology that we have in 644, 944 loader and other vehicle we're working on, even if there's a 3x cost for device level, but at system level, we could get cost neutral or cost superior and performance superior solution. So we have to take the system approach to do that. And certainly there's a risk in this new technology because on highway, like a Tesla Model 3 will be there. But in our industry, nobody has record of proving this technology on the vehicle. So there is certainly risk of doing this emerging technology. But this risk, if you mitigate that, this gives us competitive advantage that outweigh risk of being new in the field. And then we want to retain our technology leadership in electrification. With this, I would say thank you for the opportunity to Purdue team, and I will switch over to Dr. Scott Johnson.
Thanks, Bridge. So I transitioned from Purdue, where I got my PhD, over to Deere, and I think two main areas would be of interest to this group that I want to share today. So one of them is on vehicle power management, and Bridge just touched on that topic, but we'll dive in a little deeper on that. And then the other area I see controls that I've experienced when I've been at Deere is in the area of precision agriculture. So we'll see a little bit on the X-Acto merge planter and talk about where the controls really enables that vehicle and opens up opportunity for that precision agriculture. So if you can go to the next slide, you'll see that the 944 vehicle I like to describe as a big RC car. This is the largest vehicle that John Deere makes. And I don't know if you can tell the size of the cab that's in there, but that's like, those tires are as tall as I am, and I'm not a short person. So it's a pretty large vehicle, and they have wheel motors in every wheel. So really, RC car, it's that much fun to drive too, maybe even more fun. I'm still a boy at heart. So in terms of power management though, the goal once we've electrified is to get the performance that a customer needs. And kind of keep in mind that these customers are staking their livelihood on this vehicle. So their day-to-day income is coming from a vehicle like this. So it's critical that they still have the performance that you want. And with electrification, we've actually added some performance. In particular, though, for a customer, they care about how much they can put in that bucket. And the power that you can put in the fingers of that bucket really make a difference. So how can we deliver power from this powertrain to do that? So I mentioned the 4 wheel motors. There are 2 generators on this vehicle that are powered from the diesel engine. And we call this vehicle a hybrid. And you might say, again, like Bridge said, where's the battery on the vehicle? And the answer is we don't need a battery on the vehicle to do things like energy recovery. Because even though we're aggressively filling a bucket full of dirt, backing up and going forward again, we have loads that we're like places to use the power that we can regenerate. So we have hydraulic systems that are actively lifting that bucket that we can assist the engine with the energy we've recovered from the wheels. So we can improve efficiency without a battery to store it because we're still net consumers of power. So in addition to improving efficiency, being able to recapture energy, we need to make sure that the vehicle survives for 1 million hours or has that 1 million hours of no downtime in the field on various vehicles. And while doing it, drivability is critical. If an operator doesn't like the feel of the vehicle, they won't use it or they won't use it effectively. And one of the advantages of electrification and controls that we put in it is you can get full torque at 0 speed, which an engine can't typically do because we've decoupled the engine speed from the wheel speed. So by adding additional components, the whole system becomes more drivable. But that means that we still need to figure out how to use power electronics to deliver the right power at the right time. And the transients are pretty incredible on this vehicle, the amount of power that will change direction and move into other components. And so we really need advanced controls to do that better. And by better, I mean even better efficiency, even more aggressive drivability, and downsizing components to get the same performance. So the more you can put in controls, the leaner and more effective the vehicle can be. So next slide. Lean and effective is great, but John Deere vehicles don't typically live in nice, comfortable environments. The office that I'm working in is a lot different than the office that our customers are working in. So if you look in the center, this is a tractor that's about to drive into a huge puddle. So all of our components need to be ruggedized. All of our control schemes need to be adaptive to situations like this. So that means robust controls, understanding how we're going to design a control algorithm for not one set of dynamics, but an entire suite of dynamics that we'll see when the customer takes the vehicle on the road, in the field, in the mud. We also have other dynamics that we have to deal with, like buildup of corrosive materials when people clean the vehicles, things like grass clippings for our electrified golf equipment you can see in the upper left, that can cause plugging. And we have to figure out how to design the algorithms to either push through or protect the mechanical equipment so it can be cleaned and not be damaged. Extreme cold, dust, debris. So robust controls and robust power management are a really cool aspect of working at John Deere that I have enjoyed. The variety of the different applications and getting dirty going in the field is also pretty fun. Typing a couple lines of code and then feeling the vehicle move differently. Not every company you get that. So if you can go to the next slide for me, Mark. Switch gears for a second here, talk about precision ag. So the X-Acto Merge planter is our premier planter today, and it's used for row crops. Critical to these customers are the precision planting of those seeds in spacing, in depth. Everything about how that seed goes in the soil is critical to how that seed grows and then how much yield we get out of it. So corn and soybeans are typically what's targeted, but this plants other seeds as well. And to get an idea, like an average farm will have 350 million plants in it. And this planter and tractor can plant 700 corn seeds a second or 2,800 soybean seeds a second while running 10 miles an hour in a field. And if that doesn't feel fast, put yourself in a tractor going 10 miles an hour over this kind of off-road, you'll feel like it's faster than you expected. I'll put it that way. It is incredibly fast. But even while we're going that fast, we're able to keep the precision planting of those seeds at the desired 6-inch spacing or 7-inch spacing. And that's where the controls really comes in. So if Mark, you can go to the next slide, we're going to see a video here just to give you a picture of the components of this, and we'll talk through a couple of things. So yeah, go ahead and play it. So this is the X-Acto merge planter, and as it's panning around, you'll see these individual row units, we call them, that are mounted on the frame. And so here it should stop for us. So each one of these kind of self-contained robots is responsible for taking seeds, individually singulating them out, and then putting them in the ground. So it's a really nice contained system that we can design controls around, because that's the delivery apparatus. So go ahead and hit play, Mark. In a second, it'll jump back over to that. Can you move forward? Yeah, perfect. So if we kind of go into this planter a little bit more detail, you'll see how the seeds are coming ejected out of the trench here at the bottom into this nice little furrow. So we'll have electric motors that are controlling two parts of this row unit. And that's going to be what's sending those seeds out the brush. And on the right-hand side of the screen is a blade that's opening up the soil to create that trench at the exact depth you want it. And then on the left, you see those large black wheels that are closing up the soil around. So putting the seeds evenly and then closing up the wheel around it. So for controls, we need to deliver those seeds at both the right rate and consistently keeping those seeds spaced. One of the interesting things people don't always think about is if I was to drop a seed out of the back of a planter going 10 miles an hour, that seed's going to roll, right? It's got the velocity of the vehicle. So we are actually launching seeds out of the back of the vehicle at the same speed as we're moving forward, so that from the ground, we'd see it just drop. So that's all enabled by controls. So moving up, John Deere has an incredible number of sensors. On a normal 60-foot, 24-row planter, there's 300 sensors and 140 controllers, like 15,000 measurements per second. We can count the seeds as they're moving in this brush and delivering them to the ground. That gives us incredible information about the analytics of what's going into our field and allows us to do advanced controls to make sure that we're getting that precise placement in the ground. Go ahead. So I talked about the two electric motors that are controlling both the delivery of the seed with this brush, but also the singulation of the seed in the metering system. And so you'll see this come up here in a moment where you take bulk seeds and you singulate them using this meter design that includes a vacuum. And the motor is spinning this bowl and needs to accurately be putting in seeds into that brush, the rate at which matches the rate of the vehicle. Keep going. So being able to reject any disturbances as these seeds are being singulated is one of the critical things for the control algorithm in that motor. So the motors that I keep talking about will be shown here in a second. You'll see the mechanical design for how they're connected. The algorithms that I write day in and day out go inside the inverters that control that. I think Bridge did a great job sharing how the bigger inverters look. The smaller inverters are also very capable and need to survive an entire lifetime in the field. So the components again are very ruggedized. So hit play. So that's the system, the X-Acto planter. It's quite an innovation box, I think. We see this ability to control how the seeds are being delivered in such a modular sense. It really opens the door for the future where we see more and more precision agriculture, more controls that are going to enable it, more technology that we're putting on the back end of these planters. Because at the end of the day, this determines a lot of the farmer's value. This determines how much money they take home. So it's become quite an enabling technology for farmers and quite an opportunity for John Deere. So you can go ahead and finish that slide. So that's all we have from the Deere side. So I encourage you to look in research or consider working for a company like Deere, where I think controls do incredible things, both building and feeding the world. So thank you.
Wonderful. Thanks a lot, Mark, Bridge, and Scott. That was very exciting. So I think we'll move on to the Purdue faculty now, and then come back to any questions. If the audience has any questions, you can feel free to start chatting those and typing those into the chat box, and then we'll take those at the end. So I'd like to introduce the Purdue speakers now. Greg, you'll be first, so you can go ahead and start sharing your screen. So Professor Greg Shaver is a full professor, university faculty scholar, and College of Engineering Early Career Research Award recipient, and also an ASME fellow. His research program is dedicated to clean, safe, and efficient commercial vehicles, and he's made significant contributions in that space. So I'd like to go ahead and introduce Greg to give us an overview. And for the Purdue faculty, since faculty like to talk a lot, I'd like to keep the presentations to about 7 or 8 minutes if possible. And I might give you guys warnings if we're exceeding that. And you're muted, Greg.
So I'm trying to share my PowerPoint like we did at the beginning, and it's not giving me the same option. So I'm not sure
okay,
what I'm doing incorrectly here.
Is there the green button at the bottom?
There's a share screen button at the bottom, and if I click that, it says I can share a whiteboard, which is not what I want to do. Very interesting.
Oh, there you go. Oh, that's your whiteboard. Okay.
Okay, so maybe can you see? Can you see?
Jesse, maybe you need to make Greg a co-host.
Sure. Let me see if that works.
I think you need to make him a co-host. Maybe it will.
All right, try that, Greg. Are you able to stop sharing and then try again to reshare?
Sure. Oh yeah, it looks a little different now. Yeah, thank you so much, Shreyas.
Yeah, no problem.
Controls problem, right? Sorry, bad jokes. Okay, can you see my my slides? Okay, so I'm going to talk a little bit about some research collaborations underway between Purdue and Deere that hit automation and electrification for construction and agricultural equipment that Deere is bringing to market or will hopefully soon. So the first project I want to talk about is focused on farm machine automation. And what's going on here, so we have a combine harvesting grain, corn or soybeans as an example. And then every once in a while, we got to unload it into a tractor-driven grain cart. So we'd like to automate all or part of this process as a means to reduce the burden on the operator, make the work less exhausting, and also allow them to run the combine at an elevated speed without having to slow it down as we coordinate the unloading of the grain through this auger into the grain cart. So this is a project that's actually winding down. So we're in a transition mode. All the technical work that Purdue is going to do, that Deere asked us to do, we've done, and now we're transitioning the work into Deere, which is also actually a very cool part of our interaction, is to make sure that the tools and techniques we developed are getting into the hands of the Deere engineers and software folks who are going to take it to a production intent machine. So here what we're doing, let me say a little bit about my colleagues. So John Evans Professor John Evans from ABE, De Laurentiis, and Vine. We all work together with students and staff and dear colleagues. John Evans really co-advised the students with me. He really, I technically on paper led this project, but John effectively co-led it, and he's on the phone. So if there are any really difficult questions, I'm going to give them to John. So be ready, John. So here what we're looking at is the development of algorithms, robust controller algorithms for how we move these vehicles relative to each other, turn on and off the auger. It's harder than it looks to get the grain into the cart and keep it there and not spill it all over the ground. It's a challenging problem. The algorithms are robust. We have implemented them on real equipment, but first we implemented them in simulation and learned from that. So we didn't just go straight to the field with the algorithms. We used tools that we developed at Purdue in collaboration with our Deere collaborators. And that's basically, F equals MA of the vehicles, but also of the perception system. So we've done subsystem testing and algorithm development using both AI and physical model-based stereo camera, and LiDAR processing techniques to know where that grain cart is, know where the auger is putting the corn, so that we can use that in a feedback loop here. So we simulated and implemented those. Let's see here. Here's another way to look at that. So we developed first the simulation capability and then algorithms within MATLAB Simulink. So we designed our algorithms, we implemented them in MATLAB Simulink, which much of industry, that's how they push them into their microcontrollers, how they embed them. So that's a good fit. We did both experiments, but we also did a lot of virtual work. So the Unreal Engine that gamers in the audience will recognize as being a sophisticated tool for gaming visualization is also pretty sophisticated in the vehicle automation space. And so we unlocked that capability basically in order to capture the scene where the vehicles are, how they're moving relative to each other, under the action of the dynamics of both, F equals MA, if you will, as well as our algorithms, how that affected what the camera and or the LiDAR sensors, saw, if you will. And then we developed algorithms and simulated them and used that for feedback. What we implemented then on the vehicles themselves is the auto unload controls and also the processing from the actual sensors. And coupled that together with hardware testing and experiments. So we certainly didn't just do simulations. We didn't just do algorithm or perception algorithm development. And we didn't just do experiments. We worked all these things in parallel and they played off each other. So that's the first project. And that project's winding down, but we're very excited about it. We're working on another patent. We've already got one filed with our Deere collaborators. We're working on a second one now. So good stuff. There'll be some good journal papers and great thesis chapters that come out of that work too for our students. And those students are being heavily recruited right now by Deere. So it's like the perfect moon alignment of everyone's interest, and we want to keep that going. So second project, farming and construction machine electrification. So here what we're doing for a variety of different machines of relevance to Deere and its customers, we're going to save fuel at high engine loads via electrically driven exhaust gas recirculation or EGR pumping. We're going to also save fuel and improve after treatment function thermally, so it works very well at low loads via powertrain electrification, cylinder deactivation, and again, EGR pumping. So both Deere and Eaton are funders and collaborators on this, and Purdue is doing controls development and experiments here at Purdue. Project 3, this is a project funded by the US Department of Energy. This is a collaboration between the University of Wisconsin, Deere, and Purdue. Wisconsin is doing a great job of leading this effort. Purdue's focuses on model-based control systems for a downsized electrically boosted engine. We're also going to be supporting powertrain controls work that actually Scott is leading, as I understand. So it's going to be fun to work with you on that, Scott. This is basically in Bridge and Scott both motivated this wheel loader application very well. So this 644K hybrid diesel series electric 3-speed front end loader was converted from conventional to a series electric drivetrain in 2011 without energy storage. And that led to a 30% improvement in fuel efficiency, in part through the downsizing of the engine from 9 liters to 6.8. So that's work that Deere has already done, and it's a product they sell. The current effort that's being funded here by DOE that I'm describing is to allow further downsizing of the engine all the way to 4.5 liter, we hope, by incorporating energy storage into this vehicle and through the the controls and the coordinated controls of what the engine's doing and what the powertrain's doing. So very exciting. This experimental work is already starting to happen at University of Wisconsin. There will also be a vehicle implementation effort that Deere will lead. So I think that's probably my time. Thank you so much, Shreyas.
Wonderful. Thanks a lot, Greg. That was great. Our next speaker will be Hubo Kwai. So Hubo, would you mind sharing your screen? And I've made you co-host, so hopefully that'll work directly.
I think I'm still muted. Okay, that would be great. Thank you very much, Travis. So let me just share my screen.
And while you're doing that, Hubo Kwai is a professor of civil engineering and a professor of construction engineering and management here at Purdue. His main research interests are in engineering informatics and construction automation towards smart construction. One of his research endeavors is the integration of sensing and augmented reality visualization to monitor and control the excavation operation for safe urban excavation. So it's a pleasure to have Dr. Hubo Kwai here to tell us about his work.
Well, thank you very much, Travis. And good morning, everybody. This is such a great opportunity for me to present some of the past work and also some ongoing work we are working in the area of safe and precise urban excavation. The way we are doing is trying to leverage all the sensing technologies and visualization towards augmenting human operators with real-time data and information. So with this one, let me, construction and ag, they are similar but different animals. So for those of you who are relatively new, probably don't know much about the problem, let me just bring in some background data. So the problem we started with, or our motivation started with the utility strikes. Considering excavation is a 60 billion industry in the United States, but unfortunately mechanical excavation is the single largest cause to all the utility strikes, which causing hundreds of fatalities, thousands of injuries, and the billions of financial losses every year. And averagely, you end up seeing utility strikes once every minute. Mechanical excavator is also another troublemaker. That's the main contributor to struck by accidents, which means a nearby worker or gets struck by, gets knocked out by a machine. Other relevant concerns or issues including productivity, accuracy, and precision issues. So utility strikes, given its significance, the current practice is such. We call 811, digging or no digging, and get people to mark on your ground, indicate where your pipes or your buried cables are. Unfortunately, when you start excavating, when you start stripping, oftentimes those marks are gone, and all we can say is good luck if you can still remember where your pipes are. And for struck by accidents, a typical practice is we employ additional supervisors and observers on the job site, and to guide the operators. And another related technology has been a long time is the automated machine guidance. The goal is towards the precision cut. Whether it is effective or not doing that one, that's another question there. So we blame all the recurring excavation accidents on the lack of accurate data regarding your buried pipes, lack of real-time tracking of the excavator and the job site entities, because many are changing and moving around, and also lack an effective communication mechanism as well as interaction mechanism, how you interact with the equipment operator, and to make sure the person can develop a holistic situation awareness of what's going on regarding the whole process. So we are looking at this problem and proposing our solution in three compartments. The first is trying to come up with accurate and complete underground pipe data. The second part is to be able to track machine posts and job site entities. And the third piece is to look at the geospatial AR for visualization and also multi-venue interaction with the operator in real time. So with this one, the first part we did was a GPS, GPR. We use ground penetrating radar for detecting and mapping underground pipes. And in this part, we developed quite a lot of algorithms, including a drop flow algorithm for GPR signature detection, a clustering and a deep learning algorithm to actually separate the hyperbolas into different segments, and which allows us to correspond or connect different pipe orientations and directions with the signal there. And we also developed a VIP, very important point algorithm that takes care of all the different scanning scenarios where your pipes are not perpendicular to your GPR travel trajectory, and you are dealing with uneven surface. We also we also input probability and modeling to capture the uncertainties of the data that you capture from your sensors, as well as the algorithms going through. This part, we also worked on the natural language processing as well to deal with large textual documents and the plans and the drawings, to making sure that we have multiple sources of data that we can bring together into the data fusion process. So the whole idea, or the whole ultimate goal, is trying to be able to locate and map underground pipes, as well as measuring their material types and dimensions. So the second piece is to deal with the above ground, the dynamic and the moving objects there. For equipment, we look at, it's a relatively, coarse scale. We are looking at the joints, and looking at these joints as the keynotes and develop a keynote model. This also allows us to run closed form simulations in advance and come up with a large library of all the different images, and also leverage the degree of freedom concept to come up with two-pronged solutions towards the same goal, that is to track your equipment and its pose in real time. For people moving around, we're looking at a hybrid vision and a radio-based multi-worker detection and tracking system. This allows us to not just detect nearby workers, but also looking at their IDs, and putting them into the context for people who are supposed to be working nearby, or who are actually intruders that shouldn't be there. So if you recall Mark's image on construction safety, you end up with seeing pedestrians, right, and walking by near the trenching job, which is presents a big hazard to the job there. By bringing the context into the formula, such as what task you're working on, what's your job role. This allows us to interpret your goal and intention when you're on the job site, and being able to predict where you're moving. So this allows us to not just detect potential hazards in real time, actually being able to predict your hazards in advance. So the third piece is the visualization, as well as multi-venue interaction with the equipment operator. So by putting all the previous work, including the underground pipe data, the nearby workers and equipment movement, and putting them into geospatial AR, we were able to predict and detect those hazards, and being able to bring out a holistic situation view to the machine operator in real time. So you don't have any more blind spots. And the idea is that we are looking at the multiple venue interaction mechanisms, in addition to AR-based, visual annotation, or sound, spatial sound. We can also use haptic feedback, and also put on sensors on the human joints, and to mimic the resistance and things like those. So the idea is we would like to be able to realize the near real-time synchronization through a concept called the digital twin, maximize the communication effectiveness, but trying to minimize minimize the cognition load. As an operator in the field, they face extreme, tremendous pressure, right? You needed to keep a precise control. I mean, you needed to be able to cut precisely, maintain the productivity while making sure that you don't hurt anybody. Not just the people, but also underground pipes as well as nearby structure. So, and also because you can actually, digital twin concept allow us to bring your design intentions, such as your design the cutting depths and the extent into the model, visualized together with the bucket. This allows you to gauge whether you're cutting at the right place, cutting at the right depths, whether you're getting the productivity you're getting. And this also allows us to actually eliminate the observers or the people who's guiding the operation. So apparently it's going to increase the contractors' profitability as well. So leaping into the future, I mean, something we are also interested in and we are currently working on. And one is looking at further building machine intelligence in terms of excavation. A few concepts that we are exploring, including cloud-based learning and connection or pre-training your machine through simulators, and also looking at online learning as well. The other area that we're interested in pushing through is more of realizing two-way synchronization. So the previously we are talking about the monitoring, we're talking about the tracking, we're talking about the controlling. It is more of sense what's going on and come up with observations and then take actions. But actions in this way, we would like to go through the action taking or the control through the virtual environment, which means you don't need to be physically situated in the construction job site, but just to be at the remote location, and you can interact with the AR system, and the system is going to take your instructions and then get back and implement your commands in the field, sort of like a tele robotics, but it is supported or supplemented with our expert knowledge. So I don't work too much in the ag area, but one interesting direction that I'm always interested in is looking at how we can even collect more data and in the field, in the ag field, especially in the open ag field, leveraging drones. So you can have drone fly above, in between on the canopy, and also you have ground vehicle traveling around to give you a holistic assessment of your growing environment, as well as the condition of the crops. So I think with that, that's all I have.
Wonderful. Thanks a lot, Hugo. That's great. And finally, Jian, if you could share your screen.
Yes, sure.
And it's my pleasure to introduce Professor Jian Jin, who received.
Sorry, could you make me the co-host too?
Oh, sure.
That would be easier. Yeah.
I think you are. It listed you as co-host, actually.
Okay, let me try again. I can still only share the whiteboard now.
Yeah, you are listed as a co-host.
Anyway, let me try this. Do you see my screen okay?
Yes, we can see that. Perfect. An introduction. Professor Jian Jin received his PhD from agricultural engineering from Iowa State University. Prior to joining Purdue, he conducted research at DuPont Pioneer, which is now Corteva, where he was most recently a technology leader working on automatic phenotyping and sensing, and led a team for the company's hyperspectral imaging systems for automated plant screening. Dr. Jin's major research interest at Purdue is to build the next generation automatic crop plant phenotyping systems, along with machine vision, data processing, statistics, and big data modeling. So Jian, the floor is yours.
Thank you very much. So thank you for the opportunity. And before I start to talk about our crop plant phenotyping sensors, I just want to let my John Deere friends know that I had a lot of the former ties with John Deere, although I do not have any current project with John Deere, but my PhD project actually I should say my PhD projects at Iowa State University when I was a student was sponsored by John Deere, and so I was in Dr. Lietang's lab, and I was that graduate student working on the coverage path planning software development. And I also worked on putting a lot of the laser sensors, put them in arrays and try to scan the stems of the corn plants and do the population mapping in the field. And after that, I also worked with Dr. Stuart Bro at Iowa State too, and working with the Urbandale station. And I remember at that time, the station was still called Intelligence Vehicle System. And I believe that is now being led by Mark. So also worked on some stereo camera, watching the surface of the grain to automatically control the sprout. And also when I was at Purdue, my first postdoc, Suresh Amartya, he landed up later with John Deere, and I hope he's doing well right now. So anyway, today I'm just going to try to kind of show off our new plant crop sensors. So I'm a plant sensor developer, and here I'm just basically showing you the gallery of the new innovative phenotyping imaging systems we developed in the recent years. So as you can see, we have some large scale systems in both greenhouse and in the field. And also we also developed some smartphone based or self-contained imaging systems. Try to meet all kinds of needs of all kinds of customers. But basically, all of these systems are focused with one technology named hyperspectral imaging. So for those of you who are not very familiar with hyperspectral, you probably know grayscale image and color image. So, you know, comparing between these two, color image contains way much more information. You can see the green leaf, the red apple. So, you know, chlorophyll is going on here and anthocyanin is going on here. So way much more information from one band to 3 bands. However, if you keep going forward from 3 bands to hundreds of bands, you actually get way much more information. So that is why hyperspectral imaging is already well established to measure moisture, nutrient, disease, chemical stress, and all kinds of other things. And that is also why we invested a lot at Purdue to construct hyperspectral imaging facilities. So last 5 years, were very exciting time, and you know, it's really a pity during this pandemic you cannot come here, but in the future, if you have any opportunity to visit Purdue campus, I would love to tour you through these newly constructed facilities, fully automated and high throughput phenotyping systems. But anyway, just want to show you how we can use these systems and what we can do with these systems, right? So of course, we take images of the corn plants and the soybean plants. And with the hyperspectral signal, we can predict a lot of the different things. So for example, we can predict biomass or fresh weight very well. So you just need to take one scan, non-destructive. We can do this kind of very precise fresh weight prediction. And also we can predict NPK, all kinds of nutrient levels. And we can predict relative water content or leaf moisture with quite good quality as well. So with all kinds of these models, we can apply this in different kind of projects. So for example, if we want to help the breeders to compare between the genotypes, we can, for example, apply the relative water content prediction model. And in this example project, we tried the x-axis is the time dimension. So basically, from the first day we stopped watering, and the plants should become drier and drier over the days. And you can clearly see the dropping trend between the different genotypes. Each color is one genotype. And the breeders can clearly see which genotype is dropping with the fastest speed. So that means this genotype is not a good one for drought tolerance. And also beyond these models, just want to let you know, we also evolved a lot with the hyperspectral imaging technology and collaborated with the other researchers for disease and chemical predictions. So one example is that recently we developed some models to differentiate between the different modes of actions from the different herbicides. So if you spray dicamba 2,4-D glyphosate, you don't need to tell me which chemical you sprayed and how long after the spray it is. You just give me the pot. I take one scan, I can very confidently tell you which chemical you sprayed. So with that good technology, there is still some limit with those facilities, because only big companies and big universities, they can afford those technologies, right? We still want to help a lot more people. So here is the idea. Can we implement both the hardware and the software technologies from those expensive and the big facilities into a very small handheld device, so everybody can use it and with a lower price, right? So the good news is we made it happen. This is a device named LeafSpec. We just released about 2 years ago. So it takes about only 5 seconds for you to slide over a leaf. And you, after just a few seconds on your smartphone screen, you can see the very quickly, you can see all the results, nutrient and water. And each measurement is georeferenced. So imagine if, this one is in the greenhouse, but if you are scanning in the field, you can start to collect all the dots and build all kinds of maps. So another benefit of this kind of hyperspectral imaging sensor is that you get this very beautiful high resolution hyperspectral images. So, comparing this kind of sensor with drone images, drones are so popular now. This is basically a comparison between remote sensing and proximal sensing, right? So the dilemma is basically between the quality and throughput. If you fly very high, you can cover hundreds of acres every day, but you are suffering from all kinds of environmental condition, changing environmental conditions and the lower resolution and the different gesture of the leaves. One thing many people don't know is that when you rotates the corn leaf by from 0 degree to 80 degrees, for example, your NDVI measurement can be varying by 3 times. That's 300% variance. That's a terrible noise and variance. But with this kind of handheld device, ambient light is blocked, and we have the consistent lighting condition, the angle and the distance of the imaging. And also we have some of the other benefits. So yes, we made it easy for people to use, but at the same time, we produce a much higher quality with the traditional technology, and just want to show off the high resolution of this LeafSpec on a soybean leaf measurement. So we can see all those textures. And these resolutions, they are also very important in signal, because traditionally, you just average through the whole green leaf and use the average color to predict something. But actually the variance and the distribution of the nutrition and the stress on the leaf is really, really important signal. So I don't have time to elaborate too much on this, but just to tell you one conclusion is very clear. That is this kind of distribution analysis is really helping us to predict the phenotyping features much better. So just to show you, if you do that in the field, what you can get from the digital map. And I know it sounds a little evil, but sometimes in the hot summer, the students are scanning in the field, and I'm sitting in the air-conditioned office, and I can see the dots are showing up on the screen, and I know they are working, and I know when they may have some problem and the process just stopped. And immediately at any time, we can generate all kinds of these maps. And these maps are dynamically changing when we are collecting data. So, and also, we want to make things automated, because I don't want too many people to be working there. And Scott just mentioned that you like to work in the play dirty in the field. We also like to do that, but that doesn't mean it's easy, right? So I still remember that when we are, especially in the later stage of the growth stage in the field, sometimes you really need to take a big breath, cover your face, and push yourself into the bush. So that is not very easy. So we put the handheld device also onto a robotic arm, so to make it fully automated. So as you can just see, we use machine vision to automatically detect the target leaf, which is a top matured leaf for both soybean and corn. And and we can just automatically scan it. The throughput is still to be improved, but we also try to implement the robotic arm onto behind a vehicle. And I'm sorry, this is not a green and yellow vehicle, but if you are interested to put this sensor onto your RC vehicles, I'm very interested to talk with you about the future opportunities. So this is just some additional information about this technology. We're filing patents and trying to commercialize it. And this is being adopted by more and more companies now. So that's all what I have. Thank you very much.
Well, thanks so much, Jan. That was fantastic. So that comes to the end of the presentation phase, and we're a little bit over time, but that's totally fine because that allowed everybody to give their perspectives. So if anybody from the audience has any questions, this is scheduled until 10:30, so we do have a little bit of time. But while we're waiting, I think I had one question, which I think is, there's a huge amount of potential here for revolution, right? It's really, this technology is changing a lot of things. So and many of you, I think maybe all of you talked about this idea of humans and machines working together. So I wanted to throw out that question a little bit. What does the future of work in this, ag and construction space look like? What are the challenges for humans working with these machines, and what's the role that you envision for automation and humans moving forward? Now, and anybody can take that.
Mark, please go ahead. You are the right.
So the role for automation and humans working together, that's the context of the question.
Yeah, where do you see sort of, is this going to be a purely human perspective?
Great question, and it's not a simple answer, as probably many of you are aware. It's going to be varied. In our jobs that our customers are doing today, the next 5 years, let's say, we are working to, number one, make their jobs easier, but not change the jobs that much. For example, today we have lots of operators of machines, and they're managing not only getting that machine set correctly to do the job they need for the output they desire, but they are also managing the rest of their operation, whether it's grain logistics flowing out of the field to the bin sites, or trucks coming to a construction site to move dirt or asphalt. What we're going to be doing in the next 5 years, and have been engaged in, will be moving them to from that mode, offloading the settings of the machines by automating that part of it, so they can actually dial in the output of those jobs and manage their businesses and operations much better. So building trust with them to automate the settings and let them adjust the dials for the desired outputs. That's kind of the first step. As we transition to full, highly automated machines, then you'll start to see more remote supervision and managing those machines in the field, maybe from a remote position, obviously. And then maybe ultimately, you have mission plans for equipment, and they're doing even further, supervision of themselves. But
I
the
just
big
like
focus
to,
right now is, go ahead.
Sorry, keep talking, Mark. Then I'll my thought. Keep talking.
I was just going to say, the big focus right now is to offload them and build trust. If you don't start building trust from the beginning, which this is a huge user experience challenge, it all falls apart. So very critical that the tech is cool and needed, but the user experience is as valuable as the tech.
Correct.
to get
So
it right.
what I wanted to add was that if you make people life easy, they are going to adopt the technology, even if it is comes with some, what you call premium cost. Make people life easy, right? So and Mark is saying that, like a trust. So it could be a possibility that you develop advanced software and you teach the job, machine learn the job, like a very expert operator doing very high productive job out there, like high performance, but then machine learns it and then repeats it, So basically what that means is now operator is doing something, better, planning, observing, versus paying less attention to on the how I could be productive. So it could be a combination of both. And then eventually, as Mark is saying, when trust get built up, then yes, these vehicle could be remotely operated on both sides, ag and construction and other vehicles. This combination of a lot of, and that requires so much things like sensor, advanced computing, data fusion, you name it, all those points we hit in this 6 presentation that we had.
Very good. Any other perspectives on that from the Purdue team?
Hi, this is Shaoshui. Hi, Mark. And actually also a question related to human machine, this kind of working together. In one of your slides, you show a video and more like there's on construction part, there's a lot of machines and some operators working together. And I believe you more like introduce the algorithm to identify which is the which part of the machine, which part is the human operator. My question is that do you involve, for example, also the prediction of the machine trajectory and also prediction of human motions to identify their future, whether there were future conflict things? It seems to be very challenging to do it if purely based on the video or images. And, if another question is whether you guys will think about, to involve some maybe variable sensors to the human operators, and then they could actively measure the distance away from the machine, then maybe give an alert or a warning when they identify potential safety things.
Yeah, so your second point, I'll address first. Yes, vision cannot do everything we're wanting to do alone. And we're looking into multiple types of sensing, I would say, opportunities to fuse with vision. Millimeter wave radars coming into play. We're investigating in that. Ultrasonics was on the image I showed you earlier. That's going into production here. But it can't do everything we need. And so, yes, we are looking at other opportunities and identifying what is the right sensing to fuse with vision, and looking across all our applications too. That's one thing we don't want to get into is as much as we can and help is increase complexity and unique solutions for every job that our products do. You get into a complexity nightmare with managing all of these different solutions, and that really starves our R&D from a complexity management perspective. So we like to build these modules that can do the best that they need to do in each of the applications. That was kind of the first one. So yeah, we are investigating other fusing, and how you fuse those sensors is a critical thing too. That's not a trivial task either. But building architectures that are flexible for sensing inputs is what we're aimed at right now. Your first question, remind me what your first question was.
My first question is basically the more like I would say it's very challenging. You have answered my first question. It's very challenging to do any prediction of the motion just based on the images or videos.
Right.
It actually, my group, we have done a little bit about the human motion analysis from more like a control perspective, an inverse optimal control or inverse reinforcement learning perspective, by assuming the human motion is the optimal system or optimal trajectory. It's actually the method we have developed that matches the real human motion data very well. And I could have sent you the paper actually.
Yeah, that would be interesting. Some of the challenges we have with vision, Obviously, you deal with the environment variables like dust, snow, fog, rain. Those are all challenging for vision as well. But what you're talking about is predictive motion, which is interesting because even the vision systems, they're not perfect. Human eye is not even perfect in brain, but we are challenged with identifying humans consistently all the time. And we don't want to provide, we get false positives, false negatives. We don't want to over nuisance the operators, but you don't want to miss an important object that's in the path either.
Yeah, sure.
And we deal with occlusions, shadows. It is a challenging environment. And then, just do that for one piece of equipment in one job site. And then think about all the different pieces of equipment, all the different job sites we have to handle. It is a very large problem. And we're looking at synthetic data to help us accelerate data collection and things like that. So I would be interested in what you're talking about with the work you've been doing.
I think Deere also have done some about this kind of manufacturing and human motion involved. Right, Dave?
Hubo, I think you had a.
Yes, so Shasha, I think my group actually did also did some work on human movement trajectory prediction. So rather than relying on sensing directly, we are bringing the context information into the algorithms, which means when you think about the construction job site, I mean, people are moving around. They are there to do their job. So apparently, depending on the role they play, depending on the current active task they are working on, as well as the person or the machine they are collaborating on a specific task, they will follow certain patterns, and they always keep that intention in their mind. My recent PhD graduate, her PhD research is actually covering that part, and I think we could achieve. We don't have tons of data to do that, apparently capturing video data and then labeling all these images and frames is a very time-consuming part. But we did find that when you bring in your contextual information into the algorithm, could increase the accuracy by about 10 to 15%.
So in the interest of time here, we'll finish sort of the panel portion of the session here. So we thank you so much again for the panelists for a wonderful overview.